Hello everyone. In last class we discussed the introduction part of the resonance and what is the need of the resonance in the communication and what is the quality factor and what are the mathematical formulas of the quality factor for series RL and RC circuits. Okay, now let us see the series resonance circuit. Consider a series RLC circuit. These three are in series and driven by the one alternating voltage source V, and let us assume the voltage across resistor is VR, voltage across inductor VL, voltage across capacitor is C, and let us assume I current is passing through the circuit. Now what is the total impedance offered by the circuit for series RLC that can be denoted with Z, that is equal to, we know that V by I, where Z equal to R plus J into XL minus J into XC. So this is called as inductor reactance and this is capacitor reactance. If you make this J is common, R into XL minus XC. And according to the definition of the resonance, we know that at resonance, reactive part in the impedance term should become 0. That means XL minus XC should become 0. Means omega L minus 1 by omega C equal to 0. So omega square equal to 1 by LC. So Fr equal to 1 by S2 pi root LC. This is the one of the very important formula. If you want to find the resonant frequency of the series resonant circuit, F equal to 1 by 2 pi root LC. So in the series RLC circuit, resonance may be produced by either varying frequency for given constant values of L and C, or varying either L and C or both for a frequency. We can now see the Phasor diagrams of this series RLC circuit. These are the very important to understand the concept of resonance. Now let us see the here different cases how exactly we can take down this one. So this is VC and VL. We know that positive and negative, and resistance voltage VR. With respect to I am taking here three different cases: I, VL, VC, and this is VR. And third case, VL, VC, VR, and this is I. So for example, in Phasor diagram for series RLC circuit, for three different frequencies, keeping values of L and C are constant. So let us assume the voltage developed across RLC with respect to frequency, we are taking VC, VL and VR. For example, in this case, if the selected frequency is less than the resonant frequency, we know that omega L will become less than 1 by omega C. That means VL less than VC. Why? Because XL equal to omega L, X equal to 1 by omega C. So F is less than F naught. Capacitive reactance can dominate. That's why the curve is lag behind it. Now at F equal to F naught, we know that omega L equal to 1 by omega C, VL equal to VC. That's why we will get simply voltage across resistor. So whenever F is greater than F naught, omega L will become greater than 1 by omega C. That's why VL is greater than VC. That's why the curve is become voltage leads the current. So for any frequency F lower than the resonant frequency, inductive reactance is less than the capacitive reactance. So hence the voltage drop VL is less than the VC. So the current I leads the supply voltage, or we can say voltage lags the current. So as this we can call as a capacitive circuit. At F equal to 0, F equal to F naught, total omega L equal to 1 by omega C, voltage inductor equal to voltage across capacitor. This voltage cancel each other and the resultant voltage is the same as the voltage as VR. So the voltage and current both are in phase. This we can call as a resistive circuit. This we can call as a resistive circuit. This we can call as a capacitive circuit. So similarly, for any frequency F is higher than this F naught, capacitive reactance is very much less than the inductive reactance, means our inductive reactance is more than the capacitive reactance. Hence the drop voltage drop VL is more than the voltage drop across capacitor, which is VC. So the current I lags or voltage leads, we can say. This circuit we can call as a inductive circuit. So if you draw the reactance curves for this analysis, this is omega. Let us assume this is plus jx minus jx. So where this is XL equal to omega L, we can assume, and this is where x equal to 1 by omega c term. Now we have to take the at resonance part, total complete series resonance. This is at f0, both will get cancelled, reactance will become 0. This is the part where XL equal to XC. This will become when frequency is 0, capacitor reactance dominates. When frequency is above the resonance frequency, inductor reactance dominates. At resonance it will become 0. So this simply we can call it as a reactance curves. This will comes under the properties of the series resonant circuit. Now let us see what is the variation of currents, impedance, admittance with respect to the resonant frequency. Now let us take down, this is frequency and this is either voltage or current or impedance. This let us assume at resonant frequency f0. We know that in series RLC circuit, at f equal to f0, we know that I equal to V by Z0, that is equal to V by R. Normally we will get V equal to mod Z, that is equal to V by R square plus 1 by omega L minus 1 by omega C whole square, but at resonance or at resonant frequency XL equal to XC, that's why we will get I equal to V by R, or we can say Z equal to simply R. So at this frequency reactance is very less, that's why you will get the maximum current. You will get the maximum current where the impedance is very low. So now I am taking this is the current equation, this is the this is the impedance equation. So at 0 frequency, capacitor reactance is more, that's why impedance is more, either sides. Here inductor reactance is more. At resonant frequency, Z equal to R, resistance will become very less. So here the current is very less. Why? Because capacitor reactance is more, here inductor reactance is more. At resonant frequency, both reactance gets cancelled, that's why current is more. So these are the some variation of the impedance current with respect to the frequency. And if you find the quality factor for this series resonant circuit, we know that quality factor equal to omega naught L by R or 1 by omega naught RC. If you substitute omega naught equal to 1 by root LC, we will get the equation is 1 by R into root L by C. Okay, these are some important properties or parameters of the series RLC resonant circuit.